everyone, it's Katie with Rosie Reads, and I'm here for another episode of Rosie Reads. Now this week in all our content, we're going to be focusing on civil engineering and building things, and there couldn't be a better book to read this week than Secret Engineer, How Emily Roebling Built the Brooklyn Bridge. Now this book is by Rachel Dougherty, and she was the author and the illustrator, which is amazing. I mean, if you can draw pictures and write the words for a story, that's pretty multi-talented. And it's also a biography, and we've talked about biographies before in Rosie Reads, and it means it's a story about a real person. So the things in this book actually happened. Now, as always in Rosie Reads, I'm going to ask you to do two things while we're reading. Now, the first thing you're going to notice is that we're going to learn a lot of new engineering words while we're reading this book. So I want you to remember two of them and be able to tell me what they mean by the time we get to the end of the story. And I will tell you the two that I picked out too. Now, the other thing I want you to do while we're reading is to think about the four parts of the Brooklyn Bridge. The book goes over them, and we're going to go over them too when we're done reading. So, without further ado, Secret Engineer. Emily Warren was a bright, shiny spark who loved to learn. Now, as you can tell from the pictures, they're dressed differently from us, so this happened a while ago. Like many girls, she studied sewing and piano. Unlike many girls, she also studied math and science. In time, she married a spry young engineer named Washington Roebling, whose mind was just as hungry as hers. The Roebling family built bridges. Washington's father, John A. Roebling, was considered one of the greatest engineers of his time, and now he had a risky new idea. He told Washington and Emily he had designed a bridge to span the quick whirling waters of the East River and to finally link Manhattan and Brooklyn, and that's in New York City. He planned to build two colossal towers and sling a 14,000-foot web of steel cable between them to create the grandest avenue the world had ever seen. John wanted to send his son to Europe to learn about a new technology for building bridges. Emily insisted that she would accompany him. In Europe, Emily and Washington explored historic towns, tasted new foods, and studied the most recent advance in bridge building, the caisson. A caisson is like a giant open box turned upside down and sunk into the water. You can see that right there. The opening at the bottom traps air as the box sinks, so it's dry inside. This allows workers to dig deep into the riverbed to find solid rock to build upon. These caissons, once fixed to the firm bedrock, form a sturdy base for the bridge's towers, strong enough to support the structure's weight. Emily and Washington hurried back to New York, buzzing with discovery. John wove two caissons into his design and prepared to build the Great Bridge, but he died before construction began in 1870. Washington would have to take over as chief engineer. The caissons were larger than any ever made. The base of each one measured about 17,000 square feet. Just building them seemed nearly impossible, and that was only the beginning. And here are the steps. The workers build the caisson on dry land. Then they carefully float the airtight container out onto the river. Once the caisson is in place, workers sink it, displacing the surrounding water and trapping air inside. When it reaches the river bottom, workers can descend and start digging. The fifth step, as the workers dig, the caisson drops, so it keeps going down, down, down into the riverbed. Eventually, they dig past the soft riverbed and reach solid rock. Workers then fill the caisson with concrete and build the bridge's tower on top. We can see that all right here, and then over here as well. Washington soon discovered that construction inside the caissons was muddy, dark, and sweltering. After hours in the caisson every day, he returned home aching and dizzy, but he pressed on. Washington drew plans late into the night with Emily by his side. Emily heard that some of the workers were falling ill with pain, weakness, and nausea. They called it Casein Sickness. Then, in 1872, Washington, like many of his workers, collapsed on the dock, and he had to be ferried back home to Brooklyn. Weeks later, Washington still couldn't get out of bed. Emily insisted she'd be his eyes and ears, and legs, and arms. As Washington's eyesight dimmed from the Casein sickness, he dictated instructional letters to Emily, and she read construction reports to him. Washington could breathe a little easier knowing Emily would be at the work site. But Washington's words felt clunky and confusing when Emily repeated them to the engineers. She faithfully copied the terms and equations, but they seemed like foreign language. She was nervous. Construction on the bridge was only just beginning, and there was so much she didn't know. So Emily started to read. She studied bridge engineering and learned from Washington and the assistant engineers. As she studied, the mechanics of the bridge became clearer. The main parts of the bridge were the towers, the cables, the deck, and the anchorage blocks. One set of cables would be strung between the tops of the towers. They would balance the pull of other cables that would lead from the towers to the anchorage blocks at either end of the bridge. You can see all that right there. The cables create the tension force, and the towers create the compression force. A force is an invisible push or pull that acts on an object, and together these opposite forces would hold the deck upright. The more Emily learned, the more confident she felt. As time went on, she could see the drawings coming to life. She saw the steel cables swooping between the towers in what she learned was called a catenary curve, the perfect natural arc of a cable held only at its ends, like a clothesline or a jump rope. She saw the tiny ink scratches she squinted at on paper transform into huge vertical cables called suspenders, which would shift the weight of the bridge deck to the main cables. She grinned, knowing that each suspender could hold 70 tons. That is really a lot of weight. Emily learned that the Roebling design for the bridge required a new method of steelworking that had never been used before. The cables were spun from thousands of thin steel wires twisted together like invincible yarn. The rigid deck platform was steadied with steel stays, cables that striped down diagonally from the towers like sunbeams. With the tower and the deck, each diagonal line formed a triangle, the very strongest shape. No steel mill had ever been asked to make steel cables like these before, and the manufacturers wanted to meet with Washington to make sure they understood the plans. But Washington fretted. If word got out about how sick he was and that a woman was in charge, the project surely would be taken away from the Roeblings, despite all their work. Emily understood his concerns, but she insisted she could handle it. And when the meeting came, she answered all their questions perfectly. Show you that page again. More than 10 years had passed since Emily had taken the reins, and the bridge was nearly built. She saw the main cables stretching across the wide river. From her window, they looked as delicate as spider silk, but she thought proudly of the equations she'd studied to calculate the cable's strength. But just before the bridge was set to open, the public, who had never seen a bridge this large, began to worry. The skinny wires look too weak, they said. The river is too wide, they said. Everyone will fall into the water and drown. Emily insisted they were wrong. She trusted the thickness and strength of the steel cables, the stability of the diagonal stays, and the balance of the anchorage blocks against the towers. She knew the equations by heart. A week before the grand opening, Emily rode in an open carriage on the first trip across the finished bridge. She carried a rooster in her lap as a symbol of victory. When the Brooklyn Bridge opened on May 24, 1883, the two cities set off rockets and fireworks. Bands played from steamboats below all night long. Crowds gathered on both riverbanks and on boats in between to celebrate the great feat of engineering, never even knowing about the contributions of an insistent woman named Emily Roebling. The end. So Emily really taught herself how to be an engineer to help her family and her husband who got sick. And there are so many women like Emily that we just don't hear their stories, who really contributed to great STEM projects like the Brooklyn Bridge and to moving science forward to where it is today. And one of the really cool things I want you to do this week is look up some women in STEM that we don't necessarily hear about all the time and learn their stories. Now, we read about these women in Rosie Reads all the time. So one of the easiest things you can do is go back through all our videos and look for some more biographies like the one we read about Emily. We've read about the first woman doctor in the United States, the first woman to run the reptile house in the London Zoo, so many stories. So go back and hear their stories again, because the more we share their stories, the more we're going to learn about women in STEM. And the other thing you can do is look up women in STEM on Google. Just have some time with your parents if you need their help, or on your own if you can do research by yourself on the computer. And look up some women in STEM and learn their stories, because there's so many of them. And even though when we think about scientists, we tend to think about people like Albert Einstein, really, Emily Roebling is right up there too. Women have contributed to all the wonderful things that we do and see and learn about STEM. In fact, one of the first computer programmers was a woman. See if you can figure out who that was. Now, I asked you to do two things while we read this time. And the first thing I asked you to do was to think about some of those really cool new engineering words we heard in this book, and name two of them and tell me what they mean. So I want you to do that right now. Take a few minutes and tell me what were some new words you heard and what do they mean, and then I'll tell you mine. Okay, awesome. My words were casein. Now that's a whole new word. I even had to look up and learn a little bit more about it after reading the book. And remember, it's that big box, huge box that they drop down into the river, and it displaces all the water so they can dig and dig and dig down into the bedrock of the riverbed, get past all that mud, and eventually build the bridge on top of it. And the other one that is a really cool and new engineering word is the catenary curve. And essentially, that's the natural curve that happens when you hold up something like a piece of rope and let it drape, like a clothesline if you have one of those in your backyard. It's that kind of half circle shape that forms when you do that. Now, the other thing I wanted you to do while we read was to remember the 4 parts of the Brooklyn Bridge. So let's see what they were. I'm going to look it up too, just so I make sure I get them right with you. They are the towers, the cables, the deck, and that's where people go and cars go, and then the anchorage blocks. So you need all those things to distribute all the weight and hold the deck upright so people can walk across it. So let's go through them again. The towers, the cables, the deck, and the anchorage blocks. Now, we always do kind of fun projects with our Rosie Reads, and I already gave you one to look up some women in STEM, some real women in STEM like Emily Roebling, and learn about all their awesome accomplishments. And the other thing you can do, which I'm sure you can guess, given we've just read about one of the coolest bridges in the entire world, not to mention the United States, is design a bridge. And really think about supports, right? Like the casein. How are you going to get your bridge to stand up? Are you going to use cables? Are you going to use a casein? Are you going to use some kind of combination of the two? And then once you've got your design down, build it. Use fun things that you have around the house. One of the things you might have left over from Halloween, marshmallows and toothpicks, is a really fun way to build a bridge. And definitely show us in the comments, because we want to see what you've come up with. So have a great week, and remember that we'll be back on Friday to share another really cool Rosie Makes, where we get to build things together with one of our Rosie innovators. She's a high school student, and she's going to do a project with you, so it's going to be really fun. So thanks so much for tuning in. Be sure to show us in the comments your bridges, and we'll see you later this week on Friday. Bye, everyone.